Okay, so last week we were talking about Newton's second law. Okay, Newton's second law, when it comes right down to it, says that the net force acting on an object is related to its mass and its acceleration, and it can be calculated by multiplying the mass by the acceleration, or it can be calculated by finding the vector sum of all forces. Okay, now we've gone as far as looking at like a couple of questions that involve having to do the tail to head vector stuff. Okay, but mostly we've looked at problems that involve collinear vectors, okay, or a single net force that's acting on the object, okay, things like that. And that's kind of what we're going to work on today, the elevator questions, stuff like that, for the first bit of class, and then we'll start moving on to more complex stuff. I just kind of want to set in stone our understanding of this part of Newton's second law before I move on to here's a system that involves two masses and 5 forces, and figure it all out. Okay, so before we get to that kind of stuff, okay, I want to kind of go over or have you guys try some questions that are of this nature first. In the end, even the really complex questions still break down to that. Okay, everything breaks down to that. It's just how much work do you have to do to get the vector sum of all forces first? Okay, that's what becomes more and more complex as we go along. Okay, so is that ringing a bell for everybody? Okay, in your digital workbook, okay, on page 2 are a bunch of Newton's second law problems. Okay, I only want to do 6 through 16. Okay, and those are going to go, I know that sounds like a lot, like 10 questions and that's it, Coder. Oh, nice. Okay, no, it's really like the first few are quite straightforward. You got to maybe do a little bit of like an acceleration calculation and then F times A, or M times A equals F net. Okay, but as you go along, we start getting into some where you're going to have sum of all forces stuff. There's some elevator questions in there. Okay, and then a couple of kind of trickier context questions as we get down into 14, 15, and 16. Okay, so I'd like you guys working on those, and then if there's any that give us trouble, we'll go through them on the board, just ask. Okay, or if you're having trouble, I'll come around and give you a hand. Okay, but 6 through 16, okay, like I said, it's on page 2. If this is hard for you to read on the board, you can call it up on your phone on page 2. Okay, answers are there in bold, and then, yeah, if you got questions, let me know. And you know what, this is on me because I haven't addressed this yet. In all of our Newton's second law situations, the objects are accelerating, okay? Which means this formula is out. That formula calculates average velocity, not initial, not final, and cannot be used for an object that is undergoing accelerated motion. Okay? And I'm just seeing it being used a lot because it seems like the questions don't give the information that you would like. Okay, in this unit, sometimes you might be able to use this formula if you're given the right set of data. But in a question like number 6, for example, okay, I'm told that it accelerates from rest, okay, for 12 seconds, and it travels 132 meters. And I know I'm going to need the acceleration if I'm going to do this. F net equals M times A. Okay, so what's the net force acting on the car? Do I have an acceleration formula that has those 4 things in it? I do. Okay. This unit's going to involve using the acceleration formulas from last unit quite often, actually. Okay, so we have to still be pretty familiar with them. All right, since BI is 0, I can take that part out and solve for A. So I would have half of t squared over here, okay, and then I would go 132 divided by 1/2 times 12 squared. Okay, and that'll give me my acceleration. Okay, but just so you know, that whole this formula here is pretty much out for this unit. Okay, we are almost never going to be able to use that formula for anything unless the question specifically says the object is traveling at a constant velocity. Well, if it says that, what's the net force anyway? 0. If something's traveling at a constant velocity, what's its acceleration? 0. Thus, its net force, which is mass times 0, is also 0. Okay, so it's a little thing to watch out for, but just know, I didn't address that last week, so I'll own that. Okay, but V equals d over t is not a formula we can use when an object is accelerating. It calculates average velocity, not any of the initial or final ones. Okay? Any other ones giving us trouble there? Because 6 and 7 are both kind of like that. Okay, and quite frankly, this was the one I thought would start a little bit of struggle. Okay, it's an elevator question. We have to remember that first. Okay, if I throw something up in the air, vertical, it's an elevator. Okay, so in this situation, I've got the object, 15 kilograms, being thrown upwards by an applied force that I'm being asked to calculate. What other force is acting on it? Gravity. Okay, which I can calculate right off the bat because I know it's m times g, so it's going to be 15 times 9.81, so that's going to be 147.50. Yeah. 1.5 newtons. Okay. All right. What else can I calculate with the information they gave me right off the bat? Because I also have this one. Net force. I've got mass and acceleration at the start. Okay, so I can calculate this right now. All right, so I'm going to go 8.80 times 15. Okay, and that's going to give me 132, right?
Yep.
Newtons. Okay, and that's up because it does say the acceleration is up. Okay, because it says it's thrown vertically into the air. I've never thrown something vertically into the air by throwing it down. It doesn't outright say up, but it's kind of implied. Okay? All right, now that I've done that, this is kind of where sometimes people come off the rails, and that's okay because we haven't really done one like this. Okay? This 132 is the net force, but often I see people put it here, and the problem is, then they're like, but that's not what the answer is. How does that work? I just calculated the net force. Yes, you did. But remember that net force is the vector sum of the two forces involved. The applied force, which you're being asked to calculate, and the force of gravity. So that 132 is the net, not the applied. So think of it this way. If I want to throw something in the air, okay, I need to apply at least this much force, and then some. Okay, because if I only apply the 147, I'm not throwing it, I'm holding it, or moving it like this at a constant velocity, one or the other. It would be a Newton's first law situation. The net force would be 0. Okay? But in this, I'm doing this. I'm throwing it as hard as I can up in the air, which means I'm exerting way more than this. Okay? If I put 132 here, this object isn't moving upwards, it's moving downwards. So that 132 is the sum of this force I'm being asked to calculate and this one. That means that the force here is 132 newtons bigger than this force. Okay? The net force is the and then sum that I use to throw that thing up in the air. It's the extra amount of force I used when I was throwing it. Okay? Because I had more than I needed to get it moving, it accelerated. Okay? Does everyone kind of follow how that attaches to Newton's second law? Okay, so now, mathematically, what that looks like is, all right, I want to solve for FA. So I'm going to subtract FG over to the other side. Okay, so I take my 132 newtons up, which is positive, minus negative 147.15 newtons, because it's downwards. So essentially, I'm adding the two forces, and I get 279 newtons up. That should say up beside it, because without a vector, it would be wrong. Okay? So we kind of looked, I think we looked at one question like that where we had to use the net force to find one of the forces involved on Friday. So it wasn't one we've done very many of, and it was Friday, so you know, there's been a weekend in between, it's okay to forget. Okay, does everyone kind of get what we're doing there? It's still the same two steps though. It's still m times a, and then the vector sum of all forces. Just sometimes we do them backwards. Okay, that's an example of doing them backwards. Okay. Any other ones you want to go over so far?
You do 12.
12, yeah. All right, so on this one here, an object is pulled west along a horizontal frictionless surface. All right, so here's my horizontal frictionless surface. Okay, and then here's my object. All right, we're looking for the mass of the object. Okay, and it's got a steady horizontal force of 12 newtons. Okay, the object accelerates from rest to a velocity of 4 meters per second while moving 5 meters. What's the mass of the object? Okay, since that's the only force, it is then by default the net force. The vector sum of all forces says there it is because there aren't any other forces. Okay? Sure, there's gravity and normal force, but it's horizontal and it's not moving vertically, so they cancel. Okay? This force of gravity here and that normal force. They're equal and opposite, so they're gone. Okay? The only force I have that's not balanced is this one. So since I have that, okay, I know if I can get the acceleration, I should be able to get the mass. And I've got VI, VF, and D. So I should be able to do this. And get acceleration. All right, so it's another one of those ones that requires us to use our kinematics formulas. So VF squared minus VI squared over 2D is going to equal A. So we're going to have 4 squared divided by 2 times 5. Okay, so 6, doing that in my head. Okay, so 16 over 10 should give me 1.6 meters per second squared west. Okay, and then from there I should just be able to divide those two. Take my 12 divided by 1.6 and that should give me 7.5 kilograms. All right. Okay, any other ones? Okay. Yeah. Okay, how many people are done up to 16? Okay, I'll give you guys a couple more minutes and then we'll probably look at probably going to look at 13 for sure, and probably 15 as well. Okay, so I'll give you a couple more minutes on those. Okay, oh, sorry, I have a question.
I was just going to ask, is initial acceleration the exact same as acceleration?
It's the acceleration during the acting of the net force. Okay, let's have a look at number 13 here, okay? Just a standard elevator question. So the mass of the elevator is 1,200 kilograms, okay? We know that it's being pulled upwards by a force of tension that is obviously going to change depending on whether, on the movement of the elevator, okay? And obviously downwards by a force of gravity that is not going to change because it's not going to change planets, okay? So we know the force of gravity downwards is going to be 1,200 times 9.81 m times g, which is going to be 11,772 newtons. Yeah? Okay. So I've got my force of gravity downwards, and then they're telling me in part A that it's accelerating downward at a rate of 1.05 meters per second squared. So just as kind of like a self-check here, is the tension bigger or smaller than gravity in situation A? Smaller. It has to be because the object is accelerating downwards, which means the net force is also down. So the down force is bigger than the up force. All right, so what I want to calculate right now then is the net force, because I can. I have the mass of the elevator and the acceleration of the elevator. Okay, so I'm going to take my 1,200 kilograms and I'm going to multiply it by negative 1.05 because it's down. Okay. When I do that, what does that come out to, you guys, just so I don't have to wait for my calculator?
12.5
1260 maybe.
Negative 1260. All right, so I've got negative 1260 newtons as my net force. Now the question wants to know what's the tension in the cable. Well, regardless of whether the elevator is moving up or down or at a constant velocity or accelerating, okay, the F net in this situation is the tension force plus the force of gravity. Those are the only two forces acting here. Okay, everyone okay with that? Right. So I just calculated F net. I previously calculated Fg. Can I find the upward force? I can. So I'm going to manipulate this to solve for Ft, right? And that's going to be F net minus Fg. So that'll be negative 1260 minus negative 11,772. Okay, and when I do that, I should get 1.05 times 10 to the 3 newtons up, which makes sense. That is smaller than the force of gravity. Okay, so it's basically, what the elevator is basically doing is pulling upwards, but lowering the elevator. Okay, I mean, to lower something, you have to pull upwards. To drop something, you don't. Okay, and there's a big difference between lowering something under control and dropping it. Okay, if I drop it, the net force is gravity, and that's the only thing that's going to happen. You don't want that in an elevator. Okay, you want something to be lowering you gently, okay, down to the ground. All right, so that's situation A. Situation B, I got basically the same numbers, except now it's up. All right, so now instead of being negative, my net force becomes positive. So I do exactly the same thing, I just take the negative off the 1260. Okay, so now I have 1260 minus negative 11,772, which will give me 1.31 times 10 to the 3, which is now bigger than the force of gravity, so now the elevator accelerates upwards. Okay, those two are pretty straightforward. It's C, which is actually mathematically way easier, but contextually more difficult. The elevator is moving downward at a constant velocity. Does it even matter what that constant velocity is? It doesn't. It doesn't make any difference. The number is only there to throw you off. As soon as you see the words constant velocity, what's the net force? 0. What does that mean about the upward and downward force? They're the same. They have to add up to 0, right? In order to get a vector sum of 0, my upward force and downward force have to be equal, which is why you get 11,772 newtons, which then rounds up to 3 significant digits as 1.18. Okay? Is everybody all right with that? That is a very, very typical elevator question that you could see on an assignment or a quiz or something like that. Okay? Especially the part C. Right? The part C requires way less work than A and B do, but it requires a good understanding. And there's a lot of that in this unit. Okay? Not a mathematically difficult question, but an understanding the context difficult kind of question.
Like, how much work would we have to show on a question? Like,
You would have to show me that you calculated FG, maybe show me F net was 0, and then write the number. Have the free body diagram, right? Stuff like that. And that would probably only be a 3-mark question, your free body diagram, calculating FG and showing me that they were equal. Yeah. So again, that's another one, right? Like, look at how much it's out of. And like, if I just had 13A, that would have been a 5-mark question. Okay? But 13C would be a 3-mark question. Less work. So you can always, let the marks that it's out of kind of give you a hint as to, it's only 3 marks. That's givens and 1 calculation and an answer. Okay, if it's 5 marks, it's givens and a calculation and a calculation and, you know, a calculation and then mark, right? So for part A, it would be, here's your calculation. Here's your calculation, okay? Here's your diagram. Here's your net force calculation. There's your 5 marks. Your answer is your 5th mark. Okay, does that sort of make sense? All right, let's look at 16 as well, and we're going to move on here. All right, so in number 16, we got this object given a push along a horizontal surface. If the velocity of the object when it's released is 0.5 meters per second west, and the object slides 0.25 meters before coming to a stop, what is the magnitude of the force of friction? This is a contextually difficult question. Mathematically, it's simple, okay? But contextually, it's difficult because it mentions getting things started, but it's only asking about how things end. It says it's given a push and never tells me how hard it's pushed. It's because it doesn't care. It only cares what's stopping it. So in this question, okay, yes, somebody pushed the object, but all the question is worried about is this part. What's stopping the chair? Friction. What's the only force acting on the chair that matters in that situation? Friction. Does that make it the net force? What other force is acting on it? Nope. When it was released, I'm not pushing on it anymore, right? It says when it was released, it was moving at 5.5 meters per second. That means I'm not pushing it anymore. That means the only force acting on it now is friction. Gravity's there, yes, but it's canceled by normal force. The chair didn't move up or down, right? If something's on a horizontal surface, gravity is likely not going to be involved unless there's some sort of vectored upward force, okay? In this case, there's not. It just says it's moving horizontally. If it's moving horizontally, you know the forces that are vertical cancel. Okay, does everyone follow me there? So the only thing that's acting on the chair after I release it, I'm done that part. Now it's slowing. As soon as it leaves my hand, it's slowing. Okay? And so that means only friction is acting on it, which does make then friction the net force. Any situation where something is sliding to a stop, friction is the thing that's stopping it. Okay? If it's horizontal, friction is the net force because it's the only force that's acting on the object. Okay? So this is one of those context things you're going to come into all the time. Car slams on its brakes on a level road. Object slides to a stop along a level surface. Okay? A hockey player, stops on an icy surface. Okay? All of those things are friction is the only force acting on the object that matters. It's the only unbalanced force. And in that case, then it is the net force. Okay? So we are looking for the force of friction, which in this case happens to be the net force. Here's my object on the horizontal surface. Force of friction. There's no force forward. Forces up and down cancel. Vector sum of all forces says that's the only force, so it's the net force. Okay. From there, I should be able to then calculate the force of friction by going m times a. I just don't have a yet. Okay. So I know VI. I know D. And it comes to a stop. Can I calculate A with those three things? Okay, so I'm going to have 0 squared minus 0.5 squared divided by 2 times 0.25. Okay, so 0.5 squared is 0.25. Okay, divided by 2 times 0.25. All right, so my acceleration then is 0.5, actually it should be negative because I didn't do this part. Hang on, I'm going to clear that up again. Sorry, 0 squared minus 0.5 squared. I didn't do that and I should have. That gives me that, negative. Okay, divided by 0.5. So my acceleration is negative 0.5 meters per second squared. Okay. The negative is important because what's the object doing? It's slowing down. My acceleration should be negative because the only way I get a negative acceleration is if something is pulling back on the box. And that pulling back force is friction. Friction always holds you back. Okay? It's the thing that slows you down. Okay? So now that I've got the acceleration, okay, now I can go 1.0 kilograms times the acceleration, negative 0.5, and I'm going to get 0.5 newtons backwards, or negative. And negative would be fine on this one because, oh no, sorry, it's west. Released at 0.5, so this would be east. Okay, so again, did we do very much math in that question? But it was contextually difficult. Okay? We had to really see into what was going on and really interpret the question. And that is the challenge with the bulk of these questions. You're always going to be doing the same, basically, 2 or 3 things. An acceleration calculation, a vector sum of all forces, and an m times a. Always going to have at least the last 2. Okay? And those are not usually mathematically challenging. It's figuring out what to do with them that is challenging. All right. Let's have a look at what we're going to start looking at tomorrow. Okay, so a question like this looks a little different. Maybe it looks a bit intimidating, okay? But I want to ask you this. If a train is being pulled along the ground, on the tracks, level tracks, do all parts of the train, all the cars, have the same acceleration? They do. In the same way that a semi-truck with 2 trailers has this, the truck and both trailers all have the same acceleration because they're what? They're connected. Okay, I mean, imagine this. If I had a train and every car had a different acceleration, what would that look like? Or worse. Yeah, it would look like a derailment one way or the other. Okay, if I got the engine, what do they call it? Yeah, the engine. You know, Thomas, the guy that pulls the train. Okay, he's accelerating at 5 meters per second squared, and the car behind him is accelerating at 8 meters per second squared. That's a problem. That means that the car is going to pass the thing pulling it. Okay, or if the car behind him has an acceleration of 2, that means they're coming apart. Okay, every part of a train has the same acceleration. They have to. They can have different masses. That's fine. They can have different net forces acting on them because they have different masses. That's fine too. But the one thing we have to understand about any system of connected masses is that all the parts have the same acceleration. Okay? Knowing that means if I can find the acceleration of one part, I know it for all of them. Okay? And they tend to move as a single unit. Okay? So really, looking at this question, I can separate it into a 20 kilogram mass and a 10 kilogram mass, and I may have to do that. But I can also say, that this is a 30 kilogram mass being pulled by an applied force forwards and friction backwards. Okay? Because they're going to move as a single 30 kilogram unit.
Did we ever get an elevator question like this, where
Yep.
there's multiple? Because when you take the force of gravity and you multiply the weight to get the downward force, would you add both the weights together or just select one? Because that will give you a different number.
There's no hard and fast rule on it. It'll depend on what the question is asking for. Okay, like for example, tomorrow we're going to do a question that involves 2 pails full of nails, 2 buckets of nails. Okay, and so they're connected by a rope. So I'm pulling the top bucket up with a rope, but the top bucket is connected to the bottom bucket by a rope as well. So it's an elevator with 2 cars, but they accelerate upwards at the same rate. Right? So as long as I know what that rate is, I can work with either the combined total or piece by piece. Okay? Because sometimes what they're going to want to do, and what this question wants to know is, what's the tension in this rope? Okay? What they tell me is the force that's being applied, this force, is 55 newtons, okay? And they tell me that the magnitude of the force of friction on the block system is 44.1. So what I'm really looking at, okay, is this. Okay, now as a part B to this question, they're going to ask me, what's the tension in this rope? Okay, and they're going to give me one more piece of information to help me do that. Okay, so right now, can I calculate the acceleration of the system? Yeah, pretty easily, right? It's 30 kilograms, and I know the force backwards and the force forwards. Right? So I've got 10.9 newtons forwards as a net force here. Right? So F net equals 55 minus 44.1, so that's going to be 10.9 newtons forward. Okay, and if I have that, okay, I can calculate the acceleration. 10.9 divided by 30. Okay, so I've got an acceleration of 0.36 meters per second squared. Okay, now, did what we did there seem a lot easier than what you thought it was going to be when you first looked at that picture? Right? We just have to, that's why we spend so long on Newton's second law. We have to see so many different situations so that we can understand how Newton's second law applies in all of them. Okay? And that's why we have to spend so much time on it. Again, how much math was there in this question? I subtracted two numbers and then I multiplied m times a. Okay? Or sorry, I divided F net by m. Right? That was it. Nothing terribly challenging. Okay? But I had to know what to do to get there. I had to be able to see that this combines to form one 30 kilogram object. Okay? All right. Now, the second part of this question involves this situation here, question number 2. All right? So I've got same situation there. I've already calculated the acceleration. Okay? It's 0.36 meters per second squared forward. Okay, and it says the force of friction on the 10 kilogram block has a magnitude of 14.7 newtons. Calculate the tension in the rope connecting the two blocks. All right, which block should I use to calculate that? The 20 or the 10? Which one do I have more information about?
10.
The 10. Okay, because right now, I don't know how much friction is acting on the second block. I could figure it out because they told me what the total was, and then they told me how much of it was the first block. But that's extra work. Okay, I want to use the first block because I know that first block is being pulled forwards by 55 newtons, has a force of friction resisting of 14.7 newtons, and what's the other force pulling on the first block? The 20 kg block. That's the tension in the rope. The only reason there's tension in that rope is because there's 20 kilograms hanging out on the other end of it. Okay, so that is the other force. Can I calculate the net force? Okay. And can I then use that to calculate Ft? Okay, so how do I calculate the net force?
Minus 14.
No, I'm going to use that second. I'm going to use the vector sum of all forces second. I got acceleration, right? I got mass, right? Can I get net force? Okay. Okay, so m times a, 0.36 times 10 is 3.6 newtons forward. All right. So now I know what the net force is. I know what these three forces are going to add up to. Everyone follow me there? Okay. Okay, so it equals the applied force plus the force of friction plus the tension in the rope between them. Okay, I know this number, I know this number, and I know this number. All right, so I'm going to bring those two numbers over. I'm going to have F net minus the applied force minus the force of friction equals the tension. So that's going to be 3.6, that one's positive because it's forwards, okay, minus 55, also positive because it's forwards, minus negative 14.7 because friction is backwards. All right, I just did the vector sum of all forces part here, yes? Okay. All right, so when I do that, I should get 37 newtons, I believe. And so 3.6 minus 55 minus negative 14.7. Okay, negative 37 newtons. That fits. It was acting backwards on the 10 kilogram block. From the 20 kilogram block's perspective, which direction is that force? Forwards. Tension's a weird thing. Okay, its direction depends upon your point of view. From the 20 kilogram box's point of view, that's pulling it forward. From the first box's point of view, it's holding it back. Okay, in the end, how much hard math was there? I added and subtracted and I multiplied two numbers. Okay? So, don't think that this unit is about difficult math. It is really about difficult context. I'm going to say it's difficult. I am going to say that. Okay? It is. It's tricky. It takes a long time to get the experience we need. That's why we're going to spend so much time on it. Okay, quiz tomorrow. Probably elevator question, I'm thinking. Okay? Probably something like that. I'll post it at the end of the day today.